Hello. So still though, we're on electrochem, nothing crazy. Um, we're only talking about galvanic cells, and so we know that these are always spontaneous cells. And we've been talking about half reactions. So we've been doing that for a little bit now, redox reactions, where we have um, something getting oxidized, something getting reduced. But one thing that we've been talking about the last couple classes is that when we're using electrochemistry, we kind of represent these half reactions always as a reduction reaction. And then we have to use these cell voltages to see, okay, which thing is going to stay reduced and which thing is going to flip around and end up being oxidized. So here's a good example. We have a galvanic cell made up of a mercury electrode, where it's going to be mercury 2 plus aqueous gets reduced to mercury, I guess, liquid form. Um, and then the other electrode is gold, and it's going to be Au3 plus being reduced to Au solid. And we have a few values here. They give us a molarity of the gold ions. So again, the solids and the liquids never go into our Q expression. So that's why we have a concentration only of one of these ions here. And they give us the cell potential. Um, this is the non-standard cell potential. And I'm asking first off, what would the standard cell potential be? So what's the formula for a standard cell potential?
Mhm. Oh, oh,
Mm,
oh.
yeah, cathode minus anode. Yep. So the E standard is not bad. That's always how our formula is going to look. Now, the only thing that can be tricky about this problem is figuring out what is going to go at the cathode and what's going to go at the anode. So I kind of said this a second ago, but we have to use these numerical values here to tell us what is going to be reduced and what thing is actually going to be oxidized. And so going off of this, what would you guys guess is actually going to be flipped and be at the anode and get oxidized? The first one, yeah, how come?
Okay.
Yeah, smaller value, exactly. So 0.8 is less than 1.5, meaning that we can kind of say that gold is better at being reduced. So that means that really this mercury thing is going to be written like this. The more positive the reduction potential is, so that's going to be this value here, the better it is at being reduced. So the more positive one here is what's really going to be reduced. So
Fine.
yeah, I was going to get into that. It can sometimes confuse people. And so I'm only going to say this like once, but when we flip this, this potential here would really become now negative 0.8 volts. But if we're plugging it into the formula, we're not going to do that. When we're plugging it into the formula, we're only using the E reduction of both of these. So this is technically like the E um, oxidation, and we don't often talk about it in that way. So if we're doing the cathode minus anode, it's really only going to be the cathode, so the reduced thing, so 1.5 minus 0.8. No, yeah, we always use the reduction potential. Like, I would say probably don't even stress it. Like, maybe forget I even said this because what we really care about is the reduction potential. There's another formula where it's like you're simply combining the values of cathode and anode in their respective forms. And so we would get rid of the minus here, and the minus would come from this, but don't think about that. That makes sense. So the answer here is going to be 0.7 volts. And then now we're getting into some formulas that will be on your formula sheet. So that's nice. First thing I'm asking is, what is the standard free energy of this reaction? And so this is going to use a formula we talked about, I think, yesterday. So I'll say that's A. And does anyone off the top of their head remember what this formula would be?
Mhm. Minus 0.257.
That is one of the formulas. This one's going to use a different one. This one's going to use, um, yeah. So standard free energy is the Gibbs free energy. So honestly, on your test, it might say Gibbs instead of standard free energy. And when you see Gibbs, I feel like that kind of gives it away better because that's when we're going to be using this one, where we have the delta G is equal to negative N times the Faraday's constant, and that will be given to you, times E standard cell potential. So this is good. We already found this on the last one. We know what F is, it's a constant. So the only thing we really need to figure out here is what N would be. And how do we think we're going to do that?
Combined together.
Exactly. Yep. So we know that if we really were doing a redox reaction, we did good because we flipped this. And so the overall thing would look something like this. We would have um, still the mercury ions in the, sorry, whoops, still the gold ions in the reactants. So Au3 plus is good here, but then we are having the mercury liquid in the reactants as well, going to form um, the solid gold plus the mercury ions. And that means that we, to combine these together, would have to do the separate half reactions, like you said, and balance them with electrons. And so the first one here, I won't write this all out because you kind of already said it. We have 3 electrons here. And if we flipped this over here, we'd have 2 electrons on the other side. 3 times 2, whatever. The lowest common multiple is 6. So that's going to be N here. Do we all feel good about that? Cool. All right. And then if we're using the units of kilojoules, the units would be, well, let's do joules first, and then we'll convert it later. But Faraday's constant is 96,485. And then we said the E cell is 0.7. So when we put this in our calculator, it's going to end up being negative 405,237 joules per mole. If it wanted it in kilojoules, we can do that here. It's going to be negative 405.237. Should we feel good about when to use that formula, what it would be asking for? Cool. Also, as a good review, would this be spontaneous or non-spontaneous?
No. Wait, no, this is spontaneous.
Spontaneous.
Oh, yeah.
Yep. Mhm. Yeah, that's a good question. And also, another thing we always know is that galvanic cells are always spontaneous, right? So we could also go based off of that. We know that if the E standard cell is positive, it's spontaneous. So that's kind of tricky. E standard cell has to be positive for spontaneity, but delta G has to be negative for spontaneity. Balanced chemical equation. I'll do this one with you guys because I feel like we kind of already talked about this. If you know what N is, we kind of know how to do this. But um, remember, we're going to multiply the things by 2 and 3 respectively to get it to be 6 on both sides. So what that ends up looking like is we would have 2 Au3 plus 3 mercury liquid goes to form 2 Au solid plus 3 mercury ions. So this is balanced with respect to atoms and electrons. All right, and then this last one is probably going to be the most involved. So this is the formula that you said earlier, um, where we were given the concentration of one of our ions, and we're asked to find the other one, the mercury ion. So we're going to have to use that big formula that looks like this, where we have the E cell non-standard equaling the standard cell potential minus 0.0592 over N times log of Q. The other one is, what is it, like ln of Q?
Or it's like there's no negative and it's like error or something. I don't know. I'm really confused on which one. Like if we need to use them for different scenarios or if we can stick with one and like I don't know.
I always use this one, and I think you can always use this one. if it's K that's at equilibrium, and so my guess is that, let me see if I can Google this real quick. Do you guys see, like, have a formula sheet copy with you? Because whatever that is the one to use.
Is the one where it's just E cell standard equals something, is that a different, I think, than this one?
I think so. Is the one that you're talking about like look like this where you have E standard cell equals the negative 0.0592 over n ln k?
Yeah.
Does that look like it? Okay. So this is only for the standard cell potential. So if we're dealing with K, remember K is always when we're at equilibrium. Q is at any point in time. It could be at equilibrium, it could not be. So if we're at equilibrium, we're going to be solving for the standard cell potential. So you can use this formula. And maybe he would have you do this. If he did, then this would be on your formula sheet. I'm not sure. But what we know most of the time, if we're finding the standard cell potential, is to use this formula, right? The cathode minus anode. So odds are, you know, he would give you this formula if he wanted you to solve it from K, or if he wanted you to find K and he gave you the standard cell potential. But most of the time, I think you're more likely to see this one where we're using non-standard and standard cell potential. So we could maybe be given all of this and try to find the non-standard, or we're given both components, like in this problem, and we have to find Q. Mhm.
You have the value 0.0257. Like, what's the difference between that?
Instead of 0.059. Did I do this wrong?
I was doing all my homework, so E cell equals negative 0.0257 over n ln k. And I was getting all the right answers.
Um, I know that there is a formula to go from log to ln. I don't even know. I wouldn't like,
Yeah.
yeah, that's what
Why?
I think that's Euler's number. So that's what the E is.
Oh.
And I don't even like, I've never known that. So I don't think you need to worry about that. Like,
Well, it's like the same equation, it was just
it was written different.
different. It was a different constant for the
Mhm.
RT. It's because of 0.2 or something. To use the L and K, it's be a different number. It's probably. Yeah, not that. Exactly,
Yeah.
the 0.2. Yeah.
Okay. That would make sense.
To go from log, because that you're using log in the one that you showed us, but that one is, that's why I said it's 0.2.
This is the type of formula that though that would always be given to you. And so I wouldn't even stress it. Like,
Well, the only thing is that the constant, like, to where.
yeah, because right, it might be written more like this, where it's the negative NF over or no, negative RT.
To get all these physics, right? Yes. And I don't see the bottom right corner, but it's just the bottom two the things that we have left. Yeah, so it doesn't give us the constant value, it just gives us the negative RT over n f.
Okay.
Yeah, because we just memorize the content, you can use that. Okay.
I would ask him in class. Yeah, this is how I would do it. I think this is way more likely. Yeah. And again, I think you're way more likely to see this one than the other problem. And if it is an E standard, you're probably going to be able to do the cathode minus anode to get you the standard cell. Okay, sweet. Yeah.
What is that one called where you have E cell equals E cell two?
This formula here,
It's the non.
this would be, yeah, finding the non-standard cell potential. So if we had different amounts of, like if we had weird quantities, or I should say weird molarities of our different ions, um, or if we're at like, yeah, I think that's the main reason, then we would be using this one, right? Because we're finding Q instead of K. Okay, so for this one, really we're plugging in mostly. So E cell we found a second ago is E cell non-standard is given to us in the problem. So I'm going to write that 0.0 785. We found the standard cell potential. That was the 0.7 equals 0.7. We found out what n was, right? We already discussed, and that's going to be 6. So then I'm going to put all this stuff in brackets and separate log q. So over here, do I agree with that? I don't agree with that. I'm not going to put these in parentheses. The first thing I'm going to do is subtract 0.7 on both sides. So I'm going to get a calculator out. Is that okay for everyone why I subtracted this first rather than making this a parenthesis? Because technically this, I think, has a parenthesis around it. So the next step is going to be dividing by this value. I'm pretty sure. So get this is equal to, and I'm going to plug this into my calculator, 0.0592 divided by 6 is equal to negative 0.00987 times log q. And now I can divide both sides by this. And this is going to be, let me come over here for this, 62.97 log q. Do we remember how to get rid of a log? Yeah. Put it to base 10. So that cancels this out. So 10 to the power of, is that right? That sounds like a big number. Hold on. That's a, yeah, really big number. Let's see if that's right. I think I agree with that. We could have a really humongous Q. That's very possible. So let's go with it. Let's just be here. All right. So that's right. 10 to the power of 62.97, whatever. That's going to be equal to Q. And we say that Q is product of a reactant. So if we're going based off of this balanced equation that we made, the mercury ions are going to be in the products. So that's going to be numerator. And we know that that has to be raised to the power of what? If focus, that would help. Yeah, there we go. Yes. Yep, we have a 3 as a coefficient, so it's going to get raised to the power of 3. And then the other thing, we're told that the concentration is 0.6 molarity, and that's going to get raised to the power of 2. So 0.6 to the power of 2, let's see what that is negative 0.36. We're going to multiply that by this. It's still a massive number. And then the last thing we're going to do is take the cube root. Yeah, or to the power of 1/3. And that's actually where I messed up right there. So it should be
times the power of 1/3?
Yeah, so I'll do this in my calculator real quick. We have yeah. So if I first thing I do is 0.6 raised to the power of 2. That's what we get. I'm going to multiply that and then by parentheses 10 to the power of 62.97. And then I'm going to use the caret function, parentheses 1 divided by 3. And so that's going to be our answer here. This is the concentration of mercury ions, 69 point, very big value, 6.95 times 10 to the 20. Maybe I messed up making this problem. Did you get a different answer?
No, not. With, like, to the top, like right where your mouse is, to the step that one.
What? My work here is not confusing. This is a mess. Yeah, let me go through this one more time. So we found that this is our equation, right? This is where we started. E cell non-standard was given in the problem. We know what the standard is. We found that a second ago. Minus 0.0592 over n6. And ignore this scribbled out brackets. The first step we do is subtract 0.7 on both sides. Then we take, I'm going to put this in my calculator, 0.0592 divided by 6, find out what that is. That's 0.00987. That's multiplied by log Q. So we're dividing this whole thing on both sides. That we're good there. Okay, so then from there, we see that 62.97 was what we got from this. That's equal to log Q, so we did base 10 to cancel out the log. Is that okay? So because it's such a big number, that like, so if I type in 10 to the power of 62.97,
Yeah.
it's like a massive, massive number, but this thing that matters is that it's still times 10 to the 62. So at this point, we're talking about numbers that are so big. This is like, I'm going to leave it as 10 to the power of 62.97. You could go straight ahead and put this into your calculator and then use that. It should be the same answer. But either way, as long as you're like within the same multiple, like times 10 to the 20 in your answer, that's probably going to get you where you need to be on this problem. Let's see if I did this. Okay, I got the same answer doing it anyway. Okay, that's what I got. Let's see.
Oh,
There you
go. Six square is the right way.
Yep.
Okay.
Yep.
That.
And then you multiply that on both sides, so it'll be
Oh.
0.36 times this huge number. And then you'll take the cube root of whatever that is, and we get a formula from that. So that's it.
That makes sense. Okay.
So honestly, like maybe when I made this problem, I put in weird values that made the math stupid. Hopefully on your like real test, he'll give you better values. But this is a unit where you could see answers like times 10 to the 20. So don't let that be like, oh, I did something wrong. That's totally possible. Do we feel okay with this problem and using this formula here? Okay. So let's see. Do I like this problem? Which half reaction has the greater delta G? Um, so, all right, let's edit this problem. I think that I haven't used this worksheet in a while. I remember this one was weird in the past. Instead of the negative 0.271, let's say that that's positive 0.271. Okay, because I think you guys will never see a standard cell potential that's negative because galvanic cells will never have that be negative. So here's the new problem. And also this is a little bit of a weird one because I'm giving you E standard cells, but only a half reaction. So normally it'd be more like the reduction potential, but let's ignore that. Let's ignore all of that. And all I'm going to ask in this problem, and this type of thing you could see on your test, is it's a different way to apply this formula right here. So let's ignore anything weird with this. And all we're doing is plugging in what n would be in the E standard cell and seeing what's going to give us a better value or a greater value. So if this is 1 and this is 2, for 1 I get an answer of and for 2 I get. So the greater value would be actually this one because it's less negative.
And that's the 0.1531.
Yeah. Yep. And so maybe another better way to ask this would have been what's more spontaneous? And then what would we have said, 1 or 2? Go based off of these values here.
Oh,
1. Yeah. Because of this being a greater negative number.
top one is more spontaneous, but the bottom one has the higher delta T or greater delta T.
Yeah. Yeah. Again, honestly, this problem sucks for many reasons. So let's move past it. But as long as you understand how to use this formula, what you're plugging in, what n is, that's more of the issue. Yeah, for the first one, it would second one would be 2. First one would be 1. Oh my God. This is really an old worksheet. I'm having you balance a redox reaction. We don't need to do this. In fact, I don't want to make you guys do that. But we're gonna skip this. It's trauma. Okay. Uh, I used to make some weird worksheets. I'm sorry, guys. This problem is totally within your guys' wheelhouse. So take a few minutes to think about it. But I would also say that this one is too hard for what you're going to see on your exam. So we're given a balanced redox reaction, and I'm basically asking what concentration of this aqueous ion in our reactant would increase the E cell. So this is using this formula here, one we used a second ago. And so if this whole thing that's being subtracted over here is dependent on Q, we know that Q is products over reactants, then I'm basically asking what value of one of our denominator things would make E cell the greatest.
And to the volume,
The smaller the number we're subtracting overall would be better.
so you need to have,
Yeah, you got it. This is a stupid problem. I don't know what I was doing back in like 2024. Um, but yeah, no, you got it. So if we made the answer should be C. Because think about it, if we made reactants in the denominator as big as possible, that means that Q is going to be a smaller value, right? And if we're multiplying this whole thing by a smaller value, we're overall subtracting less. So it's going to be closer to the standard cell potential. Is that okay? Cool.
yeah.
This would be cruel. But now you know. I think like honestly, he used to do his in-class quizzes were a bit harder, I think, than what you guys have, which is good because you don't want to be thrown like the hardest problems right when you learned it. And so sometimes there would be like it was with Alex instead of active, and he would have some hard, yeah. Oh, it was bad. I hated it. And so we would have sometimes questions like this where the whole class would kind of get caught up. So I'm very glad it's on active now. But you guys seem to understand the logic behind it. And basically everything I did in this past session was variants of those two different formulas, this one and this one. And if you understand the like concepts behind electrode, electrochemistry and all that stuff, you should be pretty good for the quiz on Monday. But I'll do a whole cumulative review on Sunday, and that'll be with all the radioactive nuclear stuff that you're doing tomorrow. And I think that stuff is not too bad. So yeah, does anyone have any questions about this or other homework things? I know. Yeah.